Good morning, everybody. I am pretty sure that I am now sharing my screen and I hope you can hear me. First of all, I'd like to thank you all for attending our MRP webinar today. It's very nice to see so many people joining in. I'd also like to thank very much Pete Multibangan Rikatama Patria for organizing this. They do a huge amount of work behind the scene. I just turn up here and present my material, but a lot of work is done to create these webinars. And especially I'd like to thank Weera for the very nice introduction she just gave us. So I now need to get on with the presentation material. You've heard about the fact you can ask questions and so on. So let's see how we get on, and off we go. So the topic today is about measuring soil shear strength using the shear box. And I said do's and don'ts. And I hope that'll become clear as to why I have that title as we go along. This is actually the second in a series of webinars on the topic of geotechnical engineering that Pete Multibangan have organized. And as I said, we're going to look at measuring soil shear strength using the shear box. And in this particular case, we're only interested in the soil strength in terms of effective stress. And we normally refer to these with the parameters C dashed and phi dashed. And we would need these to carry out designs of almost any kind of earth structure, reinforced soil structure, slope, etc. So they are very important parameters. And in this particular case, principally, I'm looking at using these materials as fills. The next webinar, which will be next month, we shall move on a bit further and look at the principle of effective stress. And then we shall also look at measuring soil shear strength using the triaxial test. That'll be the next webinar. So there's a brief outline of the webinars we plan. We're now on the second one. And the other titles there may change slightly as I go along and we see how the material is working out. But certainly the April one will be as given in this list. A few little images, a small shear box. And the small shear box set up, ready for action. It's a nice clean picture, probably taken from a catalog. So the equipment looks very nice. And this is a large shear box. This one would be 300 millimeters by 300 millimeters. And it's pretty heavy. You can't pick that up by yourself. So you need all sorts of equipment to lift it. And here it is in position, ready for carrying out a test. And what we need to remember in the whole of this discussion today is that what we're trying to find out is the shear resistance in terms of effective stress on a particular plane. Now, of course, in a shear box, the plane is created by the action of shearing in the middle of the shear box. We know that. Is that a bad thing? Well, not at all. It actually gives us a very good indication of shear strength. And that, I think that's why this test gets used so much. And I think the reason why I have made this our second webinar topic is that when I look at geotechnical reports from Indonesia and many other places, the shear box is frequently being used to determine the strength parameters for fills. So it is therefore an important test. So who is it intended for, this webinar? And well, the aim here is really to supplement existing standards and codes of practice. And what I tell you is going to be based on an extensive experience of both carrying out and reviewing data from shear box tests. And perhaps one target is to create some kind of checklist of features and test conditions which you should look at when you are reviewing results. Now, as we go through this presentation, or this webinar, please look out for these little blue boxes, which will pop out quite a lot because they are providing additional information, and they are also posing a few questions as well. And you've already heard that there will be some 3 questions at the end of the webinar, and maybe there will be some clues in these blue boxes. So the material is aimed at civil engineers in general who have some involvement in ground engineering, which is all civil engineers really. And it might be of interest to more experienced geotechnical engineers, but the main target is looking at the strength properties of fills, in particular for reinforced soil applications, because that's the field that we work in. And of course, this is vital information when you're looking at the design of these structures. I think in particular, it's like this. I'm sure many of you will receive reports, maybe from site investigation contractors, and you'll get tables of values like the one you see there. And maybe at the end of this table, there'll be a couple of columns there where you see some shear box test results, C' and phi'. And the question then is, should you just use those values directly? Should you just take them out of the report and put them straight into your slope stability program or your finite element analysis software? Or should you maybe have a bit of a look first and make sure that these properties are suitable for the task that you're going to use them for? And I think you'll realize immediately that my answer to that question would be yes, of course you should. Some important standards I'm going to refer to a bit today. The ASTM, which is reference D3080, is for this particular test. In particular, it is for consolidated drained testing conditions, which is very important. And then there is an SNI 2813, which has the same basic title, but of course in Bahasa Indonesia. It's actually interesting that the ASTM D3080 has officially been withdrawn if you look at the website. But however, it's still an extremely good document. I think of the codes I'm aware of, it's certainly one of the best. But I see no plan yet for what they're going to do to replace it. But anyhow, that is the situation with that one. As regards any books or reading, well, this was published many years ago. It's a series of 3 books published by Ken Head, and volume 2 covers tests like the shear box. It's probably a bit old-fashioned now in some regards, but the basic information in there is extremely useful. And I certainly went back to this to help me with the preparation of some of the material in this webinar today. Now, you might say, wow, 1 hour on the shear box test. Oh my gosh. Well, I'd have to say that there's a lot to cover, and actually 1 hour may not actually be long enough, but I need to go quite quickly through this to give you some chance to ask questions and so forth at the end. But we're certainly going to look at the main issues with shear box and try and understand what you should do and what you should not be doing, and how to interpret information when you see it in reports. So the content is like this. We'll first of all, to kind of warm ourselves up, look at a typical shear box test result on dry sand, which is very straightforward conditions. And then I'm going to review 3 important issues which you need to think about when you look at shear box test results: scale effects, things to do with pore water pressure, and also relating your results to a general shear strength model. I will then look at test procedures or suggestions for various typical soil types. And finally, we'll look at verification of strength values using index tests. It's a vital final step. So when you have results from, say, a shear box test or even a triaxial test, it's a very good idea to relate them to index properties for the soil and make sure that you get a good correspondence between the two. And you've already heard at the end, there will be a quiz. There are 3 questions, and they are based on the material presented in this webinar, and there are some prizes for the winners. So let's look at this shear box test on dry sand. With any test, there's always going to be information you'd like to know about it. Now, I'm not going to read through all of that there because we're going to come back to it as we look at the results. But you'll see there, if you want to read it as I'm talking, information about the grading, the compaction condition, the size of the shear box, etc., etc. So let's actually look at the test in detail. Before we do that, here's a particle size distribution curve for the sand that's being tested. It's a FM sand, fine to medium sand. And I've also put there a red dotted line, which indicates the maximum particle size that will be tested on this particular occasion. So in this case, it's a very nice result because almost all of the material will be used for the shear box test. And then I have this little kind of animation of how the test works. So we have two graphs on the left. The upper one is going to show us shear stress, which is coming from S on the diagram, versus the horizontal displacement, that's delta H. And the lower diagram is delta V, that's the vertical movement of the shear box, also against the horizontal movement. And we're going to see a first test where we apply a normal load, which is represented by, in this case, by a particular stress there of 97.1 kilopascals. And we start the test. So we start to increase S. And if you watch carefully, when we first start, the shear box both goes horizontally and upwards. And you can see the upwards movement in the diagram at the bottom, and we call this dilation. And this is a very, very important aspect and feature of shearing, especially in granular soils like this. Anyhow, we reach a peak value of the shear stress. We carry on shearing a bit further. The shear box starts to move purely horizontally, which we can also confirm in the lower diagram. So we see quite nicely from that animation how we expect the test to run. We normally do this at several different normal stresses. There are 3 of them in this case. Then having done that, we then draw an additional diagram that looks like this, where we look at, in this case, the peak shear stress values for each of those tests, and we plot it against the normal stress values. And you've got 3 dotted points there, and we draw a line on that, which in this case I've taken down through the 0, 0 point, and we measure that angle, and in this case we're going to call it phi peak, because it's taken from the peak shear stresses. However, there is an alternative interpretation of this data, which is to take the shear stress from the point in the test where the shear box is traveling horizontally. In other words, its volume is no longer changing. And this one we normally call the phi dashed at constant volume, phi dash CV. And of course, it's going to be a lower value. And if I summarize all of that with actual numbers, you see the values there. This would be very typical for a fairly angular, well-compacted sand. So there is our typical result. Now what I'm going to do with this, I'm going to add a little table of information on the bottom right. And there are 5 items in here, which I'm going to read through to you this time, but you're going to see this repeated several times in different examples of test results. Shear box size, in this case 100 millimeters. That's both the width and the length of it. Maximum particle size tested was 3.3 millimeters. It was tested and prepared in a dry condition. The rate of shearing was quite fast, it's 0.8 of a millimeter per minute. And some kind of information about the density or the compaction condition of the soil, in this case, 98% of the maximum dry density. And if you like, this information that you see now is really what you need as a minimum to be able to review a shear box test. And you'll see as we go along, you're going to see this layout of information quite a few times for different results. And you're going to see in some cases bits are missing. But on purpose, I leave all of the items here. And sometimes, I mean, frequently you'll see the vertical movement of the shear box missing in a test, which is a great shame because that is very helpful to help you interpret the results you're seeing. Also, something you will sometimes see in shear box test reports is that the horizontal axis is quoted as strain in percent, horizontal strain. Please realize that this is incorrect. There is no strain measured in a shear box test. It's simply horizontal displacement. Sometimes it's given as relative displacement, in other words, displacement compared to the width of the shear box, but there's no point in doing that. It's far best just to look at it in displacement in millimeters or centimeters or whatever you're used to looking at. Now, let's look at the first of the 3 items I want to talk about, scale effects. And to do this, I'm going to make use of my colleague Andrew Lee's coffee mug. And his coffee mug ground coffee it's about 75 millimeters high. So if I put a large shear box nearby, it looks like this. So to scale, that would be the size of a large shear box. We saw it earlier on in the pictures with the dimensions given to you there. Whereas the standard, or I'm going to call it small shear box in this case, is normally 60 millimeters across, 20 millimeters high, and there it's drawn to the same scale. And you can see that they look very different when you look at them in that way. We'll put some dimensions on there, H for height and L and W for the plan dimensions. And then one other important piece of information is the maximum particle size, Dmax, that we're going to test in the shear box. Now, if we look at ASTM, it has these requirements. I won't read them to you. You can see them there, but it has those requirements as a limitation on the maximum particle size. So if I actually put that into the shear box, it'll be 25 millimeters in the big shear box, or large one, and it would be 3.3 millimeters in the small shear box. And I've drawn the particles to scale. But if you look further into the literature, you'll find some information published by two very well-known people, Joule and Roth. This is going back to 1987. And they were requiring that ratio, L over D max, should be greater than 50 to get a representative result. Now, if I change to that requirement, then my particles shrink down to 6 millimeters and 1.2 are still drawn to scale. So this is actually quite a nice way of getting an idea about what the particle size might look like compared to the size of the shear box. And of course, the dotted line in the middle will be the shear plane where the shearing will take place. One other point to make about this is the volume of soil in each type of shear box. So if we take the ground coffee mug again, we need about 1/3 of a cup to fill the small shear box. And really, this should be used only for fine soils and sands. And then for the large shear box, you need 64 cups. And this one would be okay up to about the medium gravel size. We will come back to those particular requirements a little bit later on, but there we are, we have them, the scale effects. Now, if you want to look at the practical application of these scale effects, this is some very interesting testing of two soil types. So now on my particle size curve, I've got a red colored river sand, which is non-plastic and no fines. And we got a well-graded gravel starting at large sizes and going all the way down to fines. They're really two very different soils, and the gravel has plastic fines. So it's been given a liquid limit and a plasticity index. Let's look at the results of these. So I'm going to use my same basic layout. So this layout we've seen already. I don't need to describe it to you in detail now, but you can see there now, for example, shear box size 300 millimeters, maximum particle size tested 2 millimeters. And in this case, the test condition is damp, rate of shearing fast, and you've got information on the unit weight and water content. But what you'll see there is that the results, first of all, the horizontal displacement has much bigger numbers now because it's a large shear box, but the peak values are reached relatively quickly. So that is for the river sand. And these are the different vertical normal stresses. If I now superimpose on that diagram the results for the gravel, they look like this. And what you'll see then is to reach peak values of shear stress, you have to travel quite a long way with the shear box before you reach there, over 40 millimeters. So therefore, it's quite clearly obvious you need a large shear box to capture the shear strength behavior, and that's only the peak strength. If you compact the same gravel to a denser condition, then what you'll see has happened is that you reach the peak values more quickly because the gravel is denser. However, you still have to travel with your shear box quite a long way to reach those peak conditions. So this is a very nice illustration of the importance of shear box size on different soil types. The next thing is about ensuring that water pressure is zero. Now, when we interpret shear box test results, we're going to use the more Coulomb equation or relationship, which is given to you there, but the shear strength equaling C dashed plus the effective stress sigma dash times tan of phi dash. But we never know what is sigma dashed. So we have to write it down as its two components. That's to say total stress and pore water pressure. Now, we know the total stress because that comes from the normal load. That is a total load, so it gives us a total stress. But then the big question is, what is the pore pressure? And this is a really important question, especially in the finer soils. Now, in the shear box, unless you've got some very sophisticated equipment, which I'm not very familiar with, but we cannot measure the pore pressure, not in the standard equipment. So what we have to do is to carry out testing to make sure that this U, this pore pressure, is either zero or very small indeed. Now, one way to do this is to test dry, which is what we saw in that first example. In other words, the soil is dry and also the shear box is dry, no water at all. Then another test condition that is frequently occurring is when the soil is tested, and I'm calling it damp. And in this case, this means that almost certainly the soil has had water added to it for compaction. But in the test procedure, the box is left dry. So the soil stays damp. Now, this can lead to great uncertainty about the U value, especially if you have a high fines content in the soil. So what we normally do to overcome this is we need to saturate the soil. And the way we normally do this is by flooding the shear box. We fill up the surrounding part with water, and that water is able to communicate. What's really important, it can communicate with the water inside the sample. So this gives a way for the soil inside the shear box to reach a stable water pressure of around about zero. Please realize that this does not mean that we're implying that the soil is going to be saturated when we use it as a fill. It almost certainly won't be. It's simply being done to make sure we know what is U. Then the third of these important things is looking at a general shear strength model and comparing our results to this model. Now, this particular one I've taken from an old British standard, the one for retaining walls, but it's a very nice model, and you'll come across this kind of idea in many other places. But you'll see there the same basic shear results that we've seen from the shear box tests. But what you'll see is that the shear strength envelope, in other words, shear stress versus normal stress, has got two parts to it. It's got a peak strength, which is the darker color, which is curved, and we've got a constant volume strength, which is the lighter color, and that is a uniform linear straight line. And the region over which we get this curvature is the region over which the soil is over consolidated. In other words, it's had a previous high pressure applied and then removed. And that's why we get this kind of behavior. So the normal envelope, especially in the peak area, is not necessarily a straight line. It might look like one, but it's going to be curved if you get the complete behavior. This becomes a bit more difficult when we move to clays, especially with a high PI, because with high plasticity index clays, we tend to find behavior changing. And we find that the shear stress goes past peak and goes past constant volume and heads down to something that we call residual shear strength. And I've changed the horizontal displacement scale to do this. So what we're looking at there is the behavior of a clay when you have shearing over a long distance, which is the picture I showed you earlier on. But that's London clay. London clay has a residual phi value about 8 degrees, 8 or 9 degrees, which is very low, of course. But this is an important thing to be aware of when you are reviewing the results from shear box tests. So I thought before leaving this, I thought I'd just take one particular point. Let's go back to this diagram. And I'm going to put on here 3 possible results from shear box tests. There they are, the red squares. Now, if I simply put that result, say, into Excel, and I add a trend line, the trend line looks like this. And the trend line is suggesting that we have a very high C dashed. And this would be rather dangerous because at low strengths, or low stresses rather, you're going to overpredict the shear strength. So we need to be very careful about this kind of interpretation when we look at shear box results. Please be aware that C dashed, as you see it there, is coming from a backward extrapolation of the data. It's not actually being measured. And of course, how can it be overconsolidated? Well, this is also induced by compaction. So when we compact to fill into the shear box, this effectively is overconsolidating it. So what I want to do now is to run through a number of different soil types and discuss some of the important issues of their testing. There are lots of words here, and I'm not going to read all of them. I've put in bold some of the important words, but the reason for having so many words is that when you receive this this presentation as a handout, you will have this fairly complete information available. So start with the fine soils, clays and silts. We can definitely use the small or standard shear box because there are no scale effects. But the big issue is pore water pressure and making sure that it is either zero or negligible, thinking back to that previous slide a few minutes ago. Pore pressure in a clay will react to the loading, both the normal load and the shear stress, and it's vital that test procedures should make sure that we keep the excess pore water pressure as low as possible. And this is going to require 3 stages: saturation, consolidation, and shearing. And this can take a long time, easily 24 hours per item. So that means 1 test, 3 days, 3 samples, 9 days. So this kind of test procedure is likely to be relatively expensive. Let me just explain what I mean by some of this. So let's look at setting up a test. So we prepare our sample in the shear box, and we normally apply a small normal load just to hold it in position. And then we fill the shear box with water, and we will leave it for at least normally 24 hours until, and you'll see, I hope by the coloring, the sample becomes saturated. Now, you won't get it fully saturated. You can't drive out all the air, especially from a fine soil. But the important thing is you have a good connection between pore water in the sample and the water outside in the shear box. So that's the saturation stage of the test. We now apply the full load, big N, and we then plot a curve or a graph of the vertical settlement versus root time. And here could be a typical example. You can also plot against log time. There are 2 ways. It's like a consolidation test, but we're generally going to pick out 1 of 3 times, either for 50% consolidation, 90%, or 100%. It depends on the code of practice you're looking at. And this is, of course, is the consolidation stage of the test. So having identified either T50 or T90 or T100, we then calculate the required time to failure in the shear stage of the test, and we take it as either of 50 times T50, 11.6 times T90, or 12.7 times T100. Now, it doesn't really matter which one you use because they're going to give you much the same result. Once we've done that, we then have to make an estimate of our displacement at failure, which we probably know after we've done a few tests accurately. To begin with, you can guess it. And then from that, we calculate the rate of shear, rate of displacement, which equals dF over TF. So quick example. Imagine we do the test and our T50 is 10 minutes, quite likely for a clay material. So our time to failure, TF, should be 500 minutes. And if we estimate that DF is going to occur after 5 millimeters of movement, then our rate of shearing or rate of displacement should be 5 over 500, which is 0.01 millimeters per minute, which is very slow. It'll take about 24 hours to do the shearing under those conditions. A word of warning here about the Indonesian standard SNI 2813, because there appears to be an error in section 711, where the TF value is given directly as T50. In other words, this formula here in the SNI doesn't have the 50 in it. It just says TF should equal T50. Now, if you follow that procedure, then your shearing is going to be 50 times too fast, which is not a good idea, as you're going to see later on in some of the examples. Anyhow, having calculated that rate of shearing, RD, or the rate of displacement, RD, we then apply the shear force and the rate of movement of the shear blocks. It's a displacement control test, will be given by RD, calculated from the consolidation stage. So that's the shearing stage of the test. So let's look at a nice result here. So this is a test on a fine sandy clay. It's pretty complete. We have the box size, it's a small shear box. Maximum size is fine sand. It was done saturated. That means both the sample and the shear box full of water. And if you look at there, the rate of shearing, it's a really slow 0.0072 millimeters per minute. So this is a very nice demonstration that you can get extremely nice looking effective stress parameters out of the shear box test, providing you do it slowly in the case of clays. Okay, nice test. Here's another one. These are some tests on silty desert soils. They're low PI, and they're classified in AASHTO as A27 soils, so that should tell you something about them. And what we see here, a reported shear strength of C equals 41 and phi equals 22. Now, what do you think about that? Well, let's have a look at the information. It's it's a 100 millimeter shear box, only got fine, so there's no problem with scale effects. But the test was done damp, in other words, not flooded, at a rate of shearing of 0.8 millimeters per minute, so very fast. So what this means is we have concerns about the pore pressure inside the shear box. And in fact, this is a very good example of something that I've actually given a special name to. I call it a high C, low phi result. And I see it many, many times. And it's coming from testing fine soils, clays or silts, in the shear box at very high shearing rates like this. Now, if you are confronted with that result, I'd suggest you simply reject it. You cannot use it for design. It doesn't make sense. However, your client or the consulting engineer might not be very happy if you simply reject it. So what you should first of all do is investigate the result and find out the reason for that kind of behavior. Now, the explanation is like this. Let's just imagine this particular soil has a C dashed of 0 and a phi dash of 27 degrees. And I draw that line on the same diagram. So the horizontal distance between those points is therefore suction in the sample. So it's the suction that's giving us the high C, low phi result. So please be aware of that. But do not reject out of hand. Please investigate first before you do so to make sure you understand why you have that kind of behavior. But here's a bit of a problem, because these are some published test standards for the shear box for clay soils. And there are 3 of them. First one, and I'll read through them quickly. Slow shear test for clay soil, rate of shear less than 0.02 millimeters per minute, or time to failure greater than 50 times T50 from the consolidation test. Exactly what I've just been talking about. So perfect for carrying out this kind of testing. Second one, consolidated fast shear test for clay soil, rate of shear 0.8 millimeters per minute. And the third one, unconsolidated fast shear test for clay soil, rate also 0.8 millimeters per minute. The second 2, T0141 and T0142, are pointless. The data you get from those will be something like the previous example. They do not provide meaningful shear strength parameters, certainly not C dash and phi dashed. So please avoid those sorts of test procedures. And if you find tests are carried out following them, please be very suspicious of the results and carefully review as we did in that last example. Here is some data from a fill soil in Indonesia. Lots of nice data there, all the information we'd like to know. Unconfined test towards the bottom, and it's got some quite high values, so it's quite a stiff clay. And we got C and Phi. And what do we see? High C, low Phi. But if we look at that particular SNI standard there, then it is for an unconsolidated fast shear test. And therefore it gives high C, low Phi. Let's move on now to the next type of soil, sands with high fines content. Now we can use the standard or small shear box. That's okay, because we're not going beyond the sand size. But the problem is with a high fines content, then you may run into similar problems as we see with the clays and silts when it comes to the issue of pore pressure. Therefore, we also need to be careful about the rate of shearing, but unfortunately in these sorts of soils, sometimes it's difficult to measure T50 or T90. But luckily, the ASTM gives some very useful guidance about suggested times of failure you can guess or estimate for this kind of soil. And it says TF should be assumed to be greater than 60 minutes if the fines are more than 5%, and greater than 200 minutes in the case of a clay sand. And that's really useful guidance, and I'd suggest you keep an eye on that one when you're looking at planning this kind of testing. As a general rule, slower is better. If you're not sure, test more slowly. Move on to clean sands. Clean sands with negligible fines, very much like the very first example I showed you. Again, the standard shear box is normally okay as long as we stay in the sand sizes only, so minimal scale effects. And you can test them dry if you can achieve adequate density. High displacement rate, rate is no problem if they're dry. But if you decide you need to add water and flood the shear box, then again, you may have to be a wee bit more careful about the rate of shearing. And again, ASTM suggests that T to failure should certainly be greater than 10 minutes when fines are even less than 5%. So that's a good piece of advice there. So here is a very nice test result. This is on a fine to medium sand, similar to the one we saw earlier on in non-plastic, and it's compacted to a very dense condition in the 60 millimeter shear box, dry, and a fast test. Very nice result, very clear dilation, very clear peak values, and a very clear constant volume behavior. What was interesting in this case is that the same sand was tested in a loose condition, which is the open dots. So first of all, you'll see there's no dilation. The vertical displacement is only downwards. So the soil is becoming compacted as you shear it. And there's absolutely no sign of a peak, but all the results end up at roughly the same constant volume condition. And I think what's so nice about this test result, it shows you so clearly the dependence of phi peak on the compacted density. So you could imagine at a range of, in this case, the density is given by its void ratio, but at a range of void ratios between 0.42 and 0.61, you could have a significant range of phi peak values. So if you're using this sand to build a structure, you've got to be very confident about the likely compacted condition when you choose the phi value for design. Let's move on to clean gravels. Clean gravels, you've got to use a large shear box, again, to minimize any scale effects. And there is going to be an issue about maximum particle size. Now, if you follow ASTM, you can go up to 30 millimeters, but I think it's a bit big. According to Joule and Roth, you shouldn't go beyond 6 millimeters. But probably somewhere in the range of 10 to 15 millimeters would be about right. And this, of course, means that in many cases, you're going to have to remove coarser particles. But again, as with the the sand, if you can get adequate compaction or density, then you might consider testing it dry. So I'm just going to show you a result here. This is for a crushed gravel. So these are nice angular particles, well graded. This is a purple colored material. I've superimposed it on the grading curves from the previous examples we looked at. And I've also added there, just to mention those dotted lines, the 75 micron limit, where we normally say the fines start below that value, and 425 microns, if you remember from our previous webinar, because below that value, that's the value we use, that's the material we use to do the Atterberg limits. This one turns out to be non-plastic. And here are the results. So jumping straight in, you'll see again, quite large horizontal displacements up to 40 millimeters because it's a large shear box, well-defined peak values and a well-defined constant volume behavior. So this is a particularly nice example. You see maximum particle size there is 14 millimeters and it was done saturated. But despite that, it was also tested quite quickly. So the testers were happy that it could be tested quickly, even though it was saturated. So it's a really excellent shear box test on crushed gravel, and it's giving the kind of phi peak and phi CV you would expect from a material like that. Now here's a topic which I think is quite important, is what I call testing the wrong soil. So here is a soil, it's a well-graded sandy gravel with a bit of fines in it, and you get a result back, and the result looks like this. Unfortunately, there's lots of information missing, but as I said, I still show everything because, or what should be there to remind us, but lots of things are missing. We've only got the peak shear stresses, and we get a phi of 35 degrees, which, well, it's not bad. But when we look carefully, we see 60 millimeter shear box, maximum particle size tested, 2 millimeters, saturated, quite fast shearing, and it was well compacted. So what about this? This means we're testing a material that's a gravel, but only up to the 2 millimeter particle size. So if we go back to the particle size curve and we remove the coarse particles, we end up testing what is essentially a fairly well-graded sand with a fairly high fines content, far away from the actual material. So we saved some money on a cheaper test, but we lost maybe 6 or 7 degrees on our phi value. And if you were designing a big retaining wall, for example, that could cost a lot of money because the difference, a difference of 6 or 7 degrees in phi would have a big effect on a retaining wall design. So do not rely on small shear box testing of gravels when you're serious about getting a representative value of phi dashed. Gravels with high fines content. Now these really represent some of the most difficult soils to test. The reason is that the coarse fraction will probably dominate the shear strength behavior, but the fines and the fine sand will probably fill up the voids and then dominate the pore water pressure response. And this is difficult. So we really do need to saturate. But then we get worried about the situation with creation of suction on shearing. I'll show you a little picture of that in a minute. And if that'll happen if you test very quickly. But the problem is with a large shear box, if you go through the full saturation, consolidation, and shearing procedure, then the duration of the test could be extremely long. And to be honest, people would rarely do it. So what do you do? Well, I think these soils are difficult. But one possibility is if you're satisfied that the coarse particles will dominate the shear strength behavior, is to actually do the test dry. You might have to remove some of the fines, otherwise it would go hard, it would kind of set inside the voids, but you could test them dry. It's a possibility, but it's a judgment you have to make when you're testing this kind of soil. This is the issue. So we're now looking at a large shear box, and we got 2 particles at roughly the right size in terms of their scale sitting there, and we start to shear it. And due to dilation, the shear box goes up. Now that dilation will tend to create a lot of suction in the finer soils within the pore spaces. And that is a problem on the shear plane. So this is why I want to highlight that particular issue in carrying out shear box testing. Here's a rather interesting test. When you first look at this one, it doesn't look bad, but it is a test on gravel and it's got some plastic fines. And when we look at the shear stress versus horizontal displacement graph, they look quite good. You've got some peaks and they drop down to lower values. But when we look at the details, it's a 60 millimeter shear box testing a gravel carried out damp with a fast rate of displacement, fairly well compacted. So you have to be somewhat curious and suspicious about a test like this. If, for example, you put a straight line on the peak strength values, you're going to predict a very high C dash, maybe 50 or 60 kPa, which is simply not reliable. Another thing that's very interesting here, you can see a red line on the lower left diagram. This is the rate of dilation, which is an amazing 3.3. What does that mean? It means that for every millimeter the shear box goes horizontally, it moves upwards 3.3 millimeters. It's going up a really steep hill. Difficult to imagine how that can happen. So you have to be a bit suspicious of this test. And you'd have to be very careful how you interpret it. So really, if you put gravels in small shear box, you're going to get some unusual or strange looking results. Then the last soil, just to mention quickly, are what I'm calling mixed or gap graded soils. Now these may not be as difficult as you think. And there are two main approaches. So if you have a gap graded soil in which the coarse particles dominate the grading, so you're going to have coarse particle rubbing on coarse particle to give you shear resistance, then you could just test them as gravels with a high fines content, and maybe even consider going dry and removing some of the fine material. But you've got to be careful. If fine particles dominate, so in other words, if you've got coarse particles in a matrix of, say, silty clay, like many glacial tills, which we don't have in Indonesia, but we have in other places, then probably the best thing to do then is to remove the coarse particles and test it as a silty clay in the standard shear box, and then follow all the normal saturation, consolidation, and slow shear procedure. I've got no pictures for that. Last things to mention. What about procedures for verifying? I mentioned this is really important. Having measured strength, then you need to use index tests to verify that your values are reasonable. And this particular little technique, which is actually published now in two of the recent British standards, which have been brought into line with Eurocode, it gives you a very simple technique. So you've got two little equations there. This is for granular soils only, where it says that the phi-CV can be taken as equal to 30 plus two more terms, phi based on angularity, or an extra bit of phi based on particle size distribution. The K there means characteristic in Eurocode parlance. And then phi peak is the same, except we add on an additional bit, phi for dilation. And then these tables give you the range of these additional bits of phi value that you can add on. So in terms of angularity, between 0 and 4 degrees that you add on, ranging from rounded to angular. When it comes to particle size, again, ranging from 2 to 4, as you go from uniform, which is to say single size material, all the way up to well graded, with some special recommendations there on gap graded soils. So for this, of course, you need to look at your particle size distribution curve. Okay, so that's dealt with the first two. What about dilation? Well, this one, in this particular recommendation, is really looking at in situ soils, and it's basing dilation on what's called the density index, which can be related to the SPT result, for example. In terms of compacted soils, you'd have to try and make this assessment in a different way. But just to show you what it looks like, let's go back to this test result. Dilation is the difference between phi peak and phi CV, and you can see over on the top right diagram, it's just over 8 degrees. Another way to look at that is to look at the inclined part of that diagram bottom left. And this one has, well, this is the rate of dilation, which in this case is 0.176. And then we can use that to calculate dilation angle, which equals B times tan to the -1 of that value. And for sands, we would normally take B around about 0.8, giving us 8 degrees, which agrees very nicely with the graph above. Would you use 8 degrees for design? You have to make that judgment. Probably not, because you struggle to guarantee that you're going to have such a huge dilation everywhere at the same time during, say, the development of a shear plane within a structure. So I'm not talking today about how you interpret. I'm just talking to you about the data which you need to have to do it. What about fine soils? Well, if you go into the literature, there are many published correlations for phi dashed, normally with the plasticity data. Now, this graph you see here is a really elegant one. It's a very nice application of the Atterberg limits, where we are relating both peak and residual shear strength. You can see there the brown and the bluish colored dots to the distance, well, to the distance above or below the A line. And I'll explain to you what I mean by that in a minute. This is actually work published by Dr. Laurie Wesley, who I'm sure many of you will have heard about, especially as I mentioned him in our last webinar with his books. But this is a very nice relationship, and I think it's a very useful one to take into account. The extreme ends of the distance above and below the A line are into some very unusual soil types. Let's not worry about those too much. The ones closer are useful. So, but it's like this. There is a typical Atterberg limit diagram and plasticity chart. So we were talking about distance above the A line, that little blue arrow, or distance below the A line. That's what that meant in the horizontal axis of that previous diagram. Very useful. Here's some more published data. These are results from various sources plotting phi dashed for clays and clay silts against the plasticity index. And you can see how in general terms, especially for the peak values, they reduce as the PI increases. And that's coming from various sources. Please be aware that in many cases, these correlations will have been derived from alluvial soils. So they may not apply to the residual soils which we have here in Indonesia. So from that, I developed this little table. It's just a suggestion where we might look at the PI, see whether we're above or below the A line to give us some indication of likely phi peak or phi CV for design of an earth structure. And normally for fills, we're going to assume that C dashed equals 0. Some codes permit you to use a small value, but many codes would recommend for fills in particular, you keep C dash to 0. And I think that's the wise advice. Sometimes for very plastic soils, we might go a little bit, but maximum will probably be about 5 kPa. So if I take my recommendations and I go back to this graph and I plot them on there, they are the little straight lines with the circular symbols. So that's the recommendations for above the A line, the lower values, and this would be where the recommendations would be for below the A line. This is just my own ideas. You won't find those published anywhere else, but they seem to fit the typical ranges of data that we see from these correlations. But just one more reminder about the fact alluvial soils, mainly for alluvial soils, and probably glacial soils. So, a few conclusions and suggestions. First of all, the shear box, although many people say it has all sorts of problems, and the triaxial test should be greatly preferred, it's still a really good test, especially for when we're recompacting fills, which can be very difficult to do with triaxial testing. And we can get very good values of C' and Phi' for a wide range of soil types, providing we carry out the test following the sorts of guidance I've been talking about in this webinar. It has the advantage of being very simple. It's a simple test. We don't require the sophistication of what's called the effective stress laboratory. Those of you who are familiar with or been to soil testing laboratories, normally there's a special room called the effective stress laboratory, and it's full of computers and all sorts of pressure control equipment and very complicated looking triaxial cells. And we don't need that for the shear box. The next webinar will be to talk more about what happens in the effective stress laboratory. But in the case of the shear box, it's not normally in that laboratory. It'll only be outside in a different area in most labs. For coarse soils, the main thing you need to think about is the scale effect, so that the maximum particle size you test should be related to the size of the shear box. And again, the standard or small shear box really shouldn't go beyond the sand size. And the large one, assuming it's 300 millimeters, should not really go beyond medium gravel, certainly not into coarse gravel. For fine soils, here the main problem is to do with the pore pressure issue on the shear plane when you're shearing the sample. And you've got to try to make sure it remains either zero or very small. And this has got to be controlled very carefully by the full testing procedure, saturation, consolidation, and slow shearing. And we need to base that rate of shearing on the consolidation stage, which we saw in detail earlier on. As I said before, if in doubt, slower is better. And the other thing to do is to be on the lookout for what I call the high C, low Phi results, and have a very careful look to see why you're getting them. I suggest when you're reviewing shear box tests, you can make a simple checklist, which can really follow the diagrams I've been showing you many times, to make sure you've checked shear box size, particle size, etc., etc. How is it tested, and so on. The rate of shearing, really important. And also, finally, I would always recommend that you verify the results you see from shear box testing against index properties, as we've just looked at briefly in the previous slides. So I mentioned there a couple of the references which I used, which were both on scale effects. I used. There are probably some more references which I shall add to the PDF version of this webinar presentation, which you will be able to receive very soon. So I'll need a few minutes to do that, but then I'll add a few more references which are helpful to that list. So this will be our next webinar. Will be on the principle of effective stress and measuring soil strength using the triaxial test. In the meantime, thank you very much for listening,